Hello pre-calculus honors students, here we are with 12.3 vector and parametric equations, and we're going to use it to describe motion in the plane. Now, let's take a look at what it means to have a vector equation of a line. Suppose that P is any point on line AB, here's line AB. Then this diagram suggests a way you could write the equation in vector format. That is, vector OP equals vector OA plus T times vector AB for some real number T. And later on we're going to see that this stands for time. The equation is called a vector equation of line AB, and AB is the direction vector of the line. So you see, now to get to any point P in the line, I can't just take OA plus AB. I have to look at scalar multiples of AB that perhaps could reach far enough, and this one does in this case. Yeah, gets you to P. But I could also multiply AB by, let's say, 5, and that would put the point way down here. I want to illustrate this on our next example, our first example, with finding the vector equation line through the points 3, 4, and 5, 5. First I'm going to do it in GeoGebra, then I'll show you how to do it by hand so you understand the concept of what's going on with this. Here's our points 3, 4, and 5, 5, and we want the vector equation of this line. So on GeoGebra, to come up with a vector equation line, first might be interested in what is this direction vector. And you can come over here and come up with vectors between 2 points. And we'll call that vector A, B. There's our direction vector. It's called U right now, and it does put in this obnoxious sort of vertical format, but it's still 2, 1. And now, remember we said about the vector equation line, we want to take constant scalar multiples of this. So we're going to need a parametric variable, and we're going to call it T. And for now, let's just have it go from negative 5 to 5 is fine. Let's just have it go by only one step at a time here. Okay, so there's our parametric variable, and it can change from negative 5 to 5. Now, we need to come up with a way of adding up these vectors and coming up with these points. So we can come up with a resultant vector that adds up 2 things. First of all, sort of our initial vector, which is OA, so let's get that on there. From oopsie, that was still in this other format. Here we go. Vector from O to A, there you go, and that's V. And let's actually rename some of these because we're going to call this, here, I want to rename that as, instead of vector U, let's call it our direction vector. Okay, that's the direction vector. And V, this is our initial vector. Or actually I'm going to call it the initial position. That's the initial. And so the whole idea of coming up with a new vector is we can say we can take vector, the initial vector, this vector, plus our parametric variable T times the direction vector. Oopsie. I think I'm just going to have to use the okay. There you go. And you get 5, 5. And that certainly makes sense that we ended up there, because that was basically taking our initial vector plus the direction vector 2, and we got to 5, 5. But now that's because we only used 1. If I change this multiplier, I come up with other vectors. In fact, now I'm going to take this vector and trace it, this resultant vector. In fact, I'm going to rename this as the vector, the point P on the line. And we can trace it turn the trace on so that when I change t around, we can see all the possible vectors that can happen, depending on what t is. And you see these lining up in a line? So that's how a vector equation works. Now, what we're going to do is call these initial vectors the starting position, and we're going to take a point and add on multiples of the direction vector to come up with other points on the line. So let's go back to our example. Here we go. Okay, first up we want to come up with the direction vector. The direction vector. And that goes from 3, 4 to 5, 5. From A to B. And so to get the direction vector AB, you're actually going to subtract the point B minus A. You're going to go 5, 5 minus 3, 4 to get this vector 2, 1. That's how we get the direction vector. Now we just need any point on the line and we're all set to go. So we can use either 3, 4 or 5, 5. So you can say xy, here's the vector equation now. Any point xy on the line will equal, and some point on the line, in this case, let's just pick the first one here, 3, 4, plus t times the direction vector 2, 1. Now you might say right away, how could this possibly be the equation of the line? And what we're going to do is break this up. And it's something called into parametric equations. And let me just back up a second here and add a page. We can say xy equals 3, 4 plus 2t times t, distributing the scalar multiplier across that vector. And so xy equals 3 plus 2t, comma 4 plus t. And so xy equals, all right, that. So now I'm going to split it up and say x equals 3 plus 2t and y equals 4 plus t. I'm doing this so you can see that I'm trying to convince you that is the equation of the line as we always did here. And if we look at this, y equals 4 plus t, and let's solve this for t. So y minus 4 equals t. Now we can substitute this y minus 4 into t over here, and we get x equals 3 plus twice t, which is y minus 4. So we get x equals 3 plus 2y minus 8. So x minus 2y equals negative 5. So there's our equation of the line. Let's check that against what we saw in GeoGebra. Okay, so the equation of our line in GeoGebra, we can actually go back to making a line through 2 points, A and B, and it tells us the equation of that line is negative x plus 2y equals 5, which I believe exactly matches, yep, x minus 2y equals negative 5. So there you go. Okay, now we've got the vector equation for an object moving with constant velocity. Because from that last example, you might have said, well, why is this any better than what we've been doing all along here with x and y? Well, as you can see, the original equation also involves this other variable t, which gives us an idea of how this is changing with respect to time, a very important thing you've all studied in physics and so forth. So here's a vector equation for an object moving with constant velocity. The position at time t is the position at time equals 0 plus t times your velocity vector. And this is how we can generate then a description of motion along the line. So let's try this first example. Here with our second example. Suppose an object which is moving with constant velocity is at point 5,3 when time equals 0 seconds, and at point B, negative 4,15 when t equals 3 seconds. Find the velocity and speed of the object, and find a vector equation that describes the motion of the object. So, here's our diagram of what's going on here. We've got our point at 5,3 and a point way up here at negative 4,15. And we want to come up with this velocity vector to describe the line. Now, unfortunately, they gave us the time gap here for 3 seconds. So when we start figuring this out, if I go from vector AB, vector AB is going to be negative 415 minus 5,3. And you get basically negative 9, comma 12. You're backing up 9 and going up 12 to go from A to B. Well, for the velocity vector, though, we want to see the velocity vector as what's happening in just 1 second. So we take for our velocity vector 1/3 of vector AB. So 1/3 of negative 9, 12, and we get negative 3, comma 4. And that's that velocity vector there, negative 3, comma 4. Now, notice the velocity is a vector. Speed is a little different, though. To come up with our speed, so we had a velocity vector of negative 3, 4, but speed is a scalar, it's the magnitude of velocity. So if velocity is written with a little arrow over it, speed is written like this, without the arrow, and it means the magnitude of the velocity. So our magnitude equation is just the square root of a squared plus b squared. Negative 3 squared plus 4 squared is equal to 5. So this you might have a better understanding of in terms of what the actual speed of the object is, 5. It's a little awkward thinking of the vector, the velocity is negative 3, comma 4, but in this component form it's going to be so much easier to work with. All right, now we also had to come up with an equation. So remember, for the vector equation, we're going to say xy equals some initial point, and we can use 5, 3 plus time times our direction vector now, negative 3, 4. So there's the equation of that line. So that answers both. We've got our velocity, which was a vector. The velocity was this vector down here. The speed we came up with is just 5, the magnitude of velocity. And the vector equation that describes the motion of the object is 5, 3 plus t times negative 3, 4. Now, vector equations can be turned into parametric equations by separating the variables. We had this vector equation last time, 5, 3 plus t times negative 3, 4. Let's change this into a parametric equation by separating out the variables. And some kids just do this all at once. Some kids like to multiply things through first, like xy equals 5, 3 plus negative 3t, comma 4t, distributing a scalar multiplier over a vector like that. And now we can do vector addition by just adding up the components, 5 minus 3t, comma 3 plus 4t. And then separate the variables. X equals 5 minus 3t, and y equals 3 plus 4t. There's our parametric equation. And that's basically when you define it in terms of a third variable, t. So here's our third example. An object moves along a line in such a way that its x and y coordinates are given at time t, are x equals 1 minus t, and y equals 1 plus 2t. That's a parametric equation. When and where does the object cross the following circle? X squared plus y minus 1 squared equals 25. Now at first you might think, oh, I've got to get this looking like we had before. I've got to get the line out of this, and then I'll intersect the line with the circle. And we've done things like that before. But the parametric form actually makes it easier to solve this algebraically. First, let's get a visual idea of what's going on. We've got a circle centered at 0, 1. So this is a circle with a center at 0, 1 and a radius equal to 5. So let's get that up on there somewhere. Circle centered at 0, 1 and a radius of 5. 1, 2, 3, 4, 5. So there's the circle. Now we want to get various points in here. So let's use our parametric trick here of looking at t. And when t equals 0, then we're going to get x and y's of 1 and 1. So at time equals 0, we got 1, 1. At time equals 1, we get 1 minus 1, which is 0 for x. We put 1 in for y, we get 3 for y. 0, comma 3. Oops, see, 0, comma 3 right there. And let's try 2. t equals 2, we get negative 1 for x, and we get 5 for y. Negative 1, 1, 2, 3, 4, 5. And we start getting a picture of what this line is going to look like. Coming in here like this, and so you can start getting a good idea where intersections are going to be. All right? Now, this graph isn't required. I just want to get the concept of what we're doing here. And we're looking for a point here in the fourth quadrant or something in the second quadrant here. So now let's go like this and get some workspace here to do this by hand. All you have to do is set up your original circle equation, and I'm going to substitute in for x and y using these parametrics. So the x, the 1 minus t, goes in for x there. So I get 1 minus t quantity squared plus, and I take the 1 plus 2t and put in for y here to get 1 plus 2t minus 1, all that quantity squared equals 25. So that's 1 minus 2t plus t squared. Plus, notice the 1's cancel, and we'll just get 4t squared equals 25. So 5t squared minus 2t minus 24 equals 0. Right, which happens to factor. That's convenient. Oh, let's unpin that now. Into 5t times t, and 24, I'm thinking 2 and 12. 12 and 2, and then I'll get 10t and 12t, so let's make this a minus and this a plus. So we get at time equals 12/5 seconds, and at time equals negative 2. We end up with some exact answers here. And then you got to plug those back into your parametric equations. Remember, x equals 1 minus t, and so that means x equals 1 minus 12/5, which is negative 7/5, and y equals 1 plus 2t, so that would be 1 plus t here is 12/5, so 1 plus 24/5 is 29/5. So we get this point at negative 1 and 2/5, comma 29/5 is 5 and 4/5. Then we get another solution at t equals negative 2. So that's at x equals 1 minus a minus 2, so that's at 3. And y equals 1 plus 2t times negative 2, so we get negative 1. So we get a point also at 3, negative 1. Let's check that in our picture to see if that looks right. 3, negative 1. 3, negative 3, sorry. Yeah. And 3, negative 3, that pretty well jibes there. Don't know if I made my circle wide enough. It was centered at, and we get the other one at negative 1 and 2/5, 5 and 4/5. Negative 1 and 2/5, 5 and 4/5. Yes, it's almost up to 6. Okay. So there you go. So we came up with those. The time when the lines are going to cross was one of the questions. When does the object cross? At 2 possible times. And where? We came up with 2 intersections on the circle. Okay. Now our last topic is how to do parametric equations of curves on your TI-9 and so forth. On the TI-9, the key tool here is going to be you've got to change to mode. And when you're in mode, you're going to be given some choices. One of the first things you see in mode is you have function, and the next choice down is parametric. and that's the one you want to pick. Get yourself in the parametric mode. Now when you go to the y equals menu, you don't see y as a function of x anymore. It says xt1 and yt1. And let's try setting up this one, 4 cosine t and 4 sine t, and see what that looks like. Okay. 4 cosine t, 4 sine t. Take a look. What does it look like on your calculator? Now the TID9, at first it might look like this. It looks almost like an ellipse. But if you go to zoom square, SQR, you'll see the true shape. And where does this come from? Well, if I take a look at these two equations now and I try and change and get them out of parametric mode, I could say, well, x squared plus y squared would equal 4 cosine t squared plus 4 sine t squared. And that would be 16 cosine squared t plus 16 sine squared t. And you get 16 times cosine squared t plus sine squared t. And that's 16 times 1. So voila, there's your equation, x squared plus y squared equals 16. Okay? Now you can tweak this and see what happens on GeoGebra. Let's give that a try. Now Dr. Barlow just showed me a little trick here that you can do in GeoGebra, and that is you can define parametric variables with a command called curve. There it is, curve, expression, and we parametric variable, start value, end value. It's perfect. So keep in mind what you have to put together here. Curve of the expression for both the variables, for both x and y. So it's cosine of t, comma, sine of t. Actually, you start with 4, right? 4 cosine t, 4 sine t, comma, parametric variables t, and we want to go from 0 up to 2 pi. And the pi is over here in the little command down here. There you go, pi. There you go, pi. And there you got your circle. It's a nice, and it gives you a nice expression of the parametric equation and so forth. Now it's very easiest for this, just change this to maybe cosine 2t. So I'm going to right click, and let's go back to object properties here and change this to sine. Let's just sneak a little 2 in here. See if that makes a big difference. It did. It makes a very strange looking curve there. It's called Lissajous curve. And let's take a look at our notes here. We tried that. There he is, Jules Antoine Lissajous. And he did some things with mirrors and tuning forks, and actually came up with something that looks like an oscilloscope way before oscilloscopes. And if you go to Wikipedia on the Lissajous curves, they've got a nice little demonstration here. There you go. This is just increasing the a over b fraction from 0 to 1 in different steps. Here's different values for a and b. And Lissajous curves in general then are when you have parametric equations, sine and cosine. Or here, it says sine of t plus delta, but then you can see how that could become a cosine. So, now, okay, all right. And we'll end there with our Lissajous curves. Flange out.